Howdy, howdy, this is Mr. Potter. In our previous video, we introduced the idea of bitmaps, the idea that we can represent an image or a graphical picture by telling the user or telling the system which pixels should be turned on using a number 1 and which pixels should be turned off by using a 0. And it's a sequence of zeros and ones that we call it a bitmap. Remember that when we talk about a bitmap, we're talking about binary digits. So B IT, that's where bit comes from. So when we talk about a bitmap, we're talking about mapping bits or mapping binary numbers, zeros and ones. What we're going to talk about in today's video is we're going to talk about how to condense bitmaps. Other ways that we can represent bitmaps aside from just telling you which pixels are on and which pixels are off. We're looking for patterns here. And the idea is that if I find enough patterns, I should be able to represent a bitmap using less memory than explicitly telling you which is on and which is off. Now, I say should because it doesn't always work that way. For one, especially with the size of the bitmaps we're doing right now, the practical ones we can do by hand, you're not going to see very much saving in memory. As a matter of fact, you might see a little bit more memory being used. And number two, the thing to remember is that if I do this encryption, I may save memory, but I may do it at the cost of processing power. In other words, it may take more processing power to actually decode this encryption or this condensing format than it would to explicitly say you're on, you're off, you're on, you're on, you're off. But we're going to go through a couple of examples of ways that we can condense bitmaps just to come up with the idea that we're looking for patterns. Remember that mathematics is the science of patterns. So we're jumping back with our letter Q that we had. And when we did the letter Q in our previous video, we talked about how this was off, off, on, off, off. So we talked about this as a series of ons and offs. What I want to do is I want to know how many ons and offs we have in a row. So if I look at this first row, there are no ons, and then I have 2 off. Then I have 4 on, then I have 2 off. So I could represent this row as a 0, followed by a 2, followed by a 4, followed by a 2. If I look at this row, I have no ons, 1 off, 1 on, 4 off, 1 on, 1 off. So I could represent this row as 0, 1, 1, 4, 1, 1. This row here I have 1 on, 6 off, 1 on, and 0 off. So I could say this row is 1, 6, 1, 0. This row is going to be exactly the same as the previous row, 1, 6, 1, 0, as is this fifth row here, 1, 6, 1, 0. In this row, I've got 1 on, 4 off, 1 on, 1 off, 1 on, 0 off. So I have 1, 4, 1, 1, 1, 0. 1, 4, 1, 1, 1, 0. This row I have no on, 1 off, 1 on, 4 off, 1 on, 1 off. So this would be 0, 1, 1, 4, 1, 1. And finally, this last row is no on and 2 off, 4 on and 1 off, 1 on and no off. So I have 0, 2, 4, 1, 1, 0. And it's important to note that I have a 0 here at the beginning and a 0 here at the end, and that's really the most zeros that I can have. I'm never going to look at this and try and say, well, I have 2 on and then 0 off and then 2 on. I'm never going to do that. So one of the things that I notice is that, well, zeros will only happen at the start or an end of a row. So that's an important distinction to make here. That's one way that we can check to see if we've made an error. The only time that I should ever have a 0 is at the start or the end of a row, or possibly both. So that's one way to do error checking. Another way to do error checking is that these have to come in pairs. In other words, on and off has to come in pair, on and off. So I should have an even number of values in each row. Each row should have an on-off pair. And if I don't have pairs, if I have an odd number of numbers representing this bitmap, then I know that I've made an error. And the third thing that we have to check this is that each row has to add up to 8, because each one of these rows has 8 pixels, or 8 bits. So each row should only have a total of 8. Even in this row where I have 1 and 4 make 5, and 1 more makes 6, and 1 more makes 7, and 1 more makes 8. This entire row has to add up to 8. As a matter of fact, all of these rows have to add up to 8. And if I ever find a row that doesn't add up to 8, I'm in trouble. So I want to do another example of this. So we're going to jump over here to the letter R, which we dealt with last time. And so if I wanted to write this, I would look at this and say, okay, here I've got 5 on and 3 off. So I could say 5, 3. Notice that it is a pair, and this row does add up to 8. And I don't have any zeros in the middle. They're either in the front or in the back. The next row I have is 1, 4, 1, 2. So I could write this all in a row if I wanted to, and be real easy for me to break it apart. This next row is also 1, 4, 1, 2. Because I know that each row has to add up to 8. So I just look and see, do these add up to 8? Does the next group add up to 8? Does the next group add up to 8? So that's our error checking technique again. Notice here I've got another 5 and 3, so 5 and 3. Here I've got 1, 2, 1, 4. And again, each one of these groups adds up to 8. Here I've got 1, 4, 1, 3, 1, 3. Then I have 1, 4, 1, 2, and then I have one more 1, 4, 1, 2. So again, the things we talked about, we said that these things had to be in pairs. Notice that they always come in an on-off pair. And they all add up to 8. 5 plus 3 is 8. 1 plus 4 plus 1 plus 2 is 8. 5 plus 3 is 8. 1 plus 2 plus 1 plus 4. 1 plus 3 plus 1 plus 3. All of these groups add up to 8. And I never have zeros except at the beginning or end of a row. In this case, neither, because we have no zeros. So this is another way of doing this. Now the thing to remember is that just because I'm using fewer numbers, I'm using fewer than 64 numbers, doesn't necessarily mean that I'm saving any spots. But one thing that is interesting to remember is that these are really octal numbers. These are really base 8 numbers. That's the only time that I'm ever going to get a situation where I have all of these numbers will always go from 0 to 8. So octal works very well in this situation. So I can think of each of these being 3 bits. So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48, 51, 54, 57, 60, 63, 66, 69, 72, 75, 78, 81. So this would use 81 bits, which is a problem because a bitmap would only use 64 bits. But there are patterns in here. Notice that some of these rows are repeating. And so it would be really easy if I was to take the rows that were repeating and kind of use those to save time. Notice that row 1 and row 4 repeat. Notice that actually, these are exactly the same as the black ones we had. So rows 2 and 3 and 7 and 8 all repeat. So later on in this video, we're going to talk about how to use that repetition to really save us some time. But what I want to do first is I want to talk about if I'm given a string of digits, can I reproduce the graphic? So we're going to do that next. So here are my ons and offs. So notice that this is supposing to say I have 1 on and 5 off. So 1 on and then 5 off, and then 1 on and 1 off. Here I have 2 on, 3 off, 2 on, and 1 off. Then I have 1 on, 1 off, 1 on, 1 off, 1 on, 1 off, 1 on, 1 off. Here I've got 1 on, then 2 off, 1 on, then 2 off, 1 on, and 1 off. Then I've got 1 on, 1, 2, 3, 4, 5 off, 1 on, 1 off. And these last rows are repetitions of this fifth row. And I end up with the letter M, just like we did in our previous video. But this is just another way of representing it. And again, if we notice that these are all octal, then we kind of have that idea that we could group each of these in groups of 3 bits. And again, as I mentioned at the beginning of this video, this isn't necessarily a way of saving memory, although in some bitmaps it would. This is just another way of compressing, or another way of representing these bitmaps using patterns. So there's one other thing that I want to talk about today, and that's that idea that if I could use repetition, then I'd be okay. Now, I talked about this string of off and ons. Let's try this one more time. So I've got a 7 and a 1. Remember, I have to look at these at pairs or groups that add up to 8. So I need 7 on and 1 off. Then this next group of 8, 1, 5, 1, 1. So 1 on, 5 off, 1 on, and 1 off. Then I've got 1, 2, 1, 4. So 1 on, 2 off, 1 on, and 4 off. Then I've got 4, 4 right here. That's another pair that adds up to 8. So 1, 2, 3, 4, 1, 2, 3, 4. Then I've got 1, 2, 1, 4, which is exactly the same as the third row. I've got 1, 7, so 1 on and 7 off. This is exactly the same, 1 on and 7 off. And then I've got 2 and 6, so 2 on and 6 off. And what I end up with is the letter F. And notice that this letter F has the serifs on it, those little tags that you see on some letters, like in the newspaper, that makes them easier to read words as a group because they kind of look like they go together, almost like cursive. And again, you notice that all of these digits that we're talking about here all lie in that 0 to 8 range, so they're very well represented in octal, mainly because our bitmap has 8 columns. So I want to go to this idea of pattern recognition. So I want to condense by repeating blocks. So when I look at this, I notice that some of these blocks repeat. So I know that this group of 4 blocks here is exactly the same as this group of 4 blocks here. I notice that this block of 2 blocks is exactly the same as this block of 2 blocks. I notice that this block here is exactly the same as this block here. And I notice that all of these blocks are all the same. What I'm doing is I'm looking for patterns. I'm looking for things that are all the same. Now, this block really doesn't seem to match any group of 4, any of the 2 by 2 regions, nor does this one. So those are kind of singletons. They're standing all alone. But notice that my first block that I was dealing with, if I was to write this as a bitmap, I would have 0, 0, 0, 1. 0, 0, 0, 1. This 2-bit map, I would write that as 1, 1, 0, 0. And this 2-bit map is exactly the same, so I don't need to repeat it. This 3-bit map is off, off, on, off. So my 3rd-bit map is 0, 0, 1, 0. 4 is blank, and what's really nice is that that's the one that shows up the most in my bitmap, so it's going to be very convenient for me. 5, I'm looking at this, it's 1 on, and then nothing, 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 so 1, 0, 0, 0. 6 is 1, 0, 1, 0. And 7, I don't have a 7, so this is it. So now if I wanted to represent this, I'm representing it not as a series of ons and offs, but which one of these blocks do I see and which order. So I see a 1 and a 2 and a 2 and a 3. So 1, 2, 2, 3. Then I see 4, 4, 1, 5. So 4, 4, 1, 5. 4, 4, 6, 4. So I see 4, 4, 6, 4. And then I see 4, 4, 3, 4. So I have 4, 4, 3, 4. So this is actually a representation of my bitmap, not as bits, but as blocks that we saw some repetition in, these patterns that we're recognizing. So if I was to go down and write this as a string of digits, so my first one was 1, 0, 0, 0, 1, 2, 1, 1, 1, 0, 30010, 40000, 51000, 61010. Then I'd have the 1 2 2 3 4 4 1 5 4 4 6 4 4 4 3 4. Notice that this starts with a 1 and then I've got a group of 4. Then the next number is 2 and I've got a group of 4. The next number is 3, then I've got a group of 4. The next thing is 4 and I've got a group of 4 and a group of 4 and a group of 4. But 6 is the last block. This next block here isn't a 7. So now I know that once I'm no longer increasing this number, which was 1, and increased by 1s up to 6, because it wasn't a 7, I know that these should go in groups of 4. Again, we're looking for patterns, and this idea that we're going to see groups of 5 where the first number increases until the first number no longer increases. After that, we should be looking at groups of 4. This is another issue of parity. In other words, the idea that the pattern will let us know that if the pattern is ever broken, we know an error happened. And it's just like we were talking about on our first slide, where if I ever saw a 0 in the middle of a block, I know something was wrong. If I ever found out that I didn't have an even number of digits, I knew something was wrong. So if I ever have 5, 5, 5, 5, 5, and then I don't have 4s at the end, or if I have more than the groups of 4s that I need, I know something has happened. And this isn't going to catch every error, but this is going to catch some of the most glaring and obvious errors. So if I am downloading or uploading a file and one bit ends up getting mixed up, this is going to find that error. And it's only if a lot of bits are mixed up in a very particular way am I going to run into something where my bitmap might be corrupted. This is kind of a self-fixing algorithm. We're going to talk more about parity in tomorrow's video. But what I want to do is I want to kind of work backwards here, this idea of a string of offs and ons. So I'm looking at my 1, and of course I've got a 1 right here. 1 is no, yes, no, no. So this is what a 1 looks like. So wherever I see a 1, I know I should see that. A 2 is going to be yes, yes, no, yes. So I'm going to see this type of shape. This is going to be this type of shape. A 3 is going to be 1, 1, 0, 0. A 4 is going to be, by coincidence, the same blank that it was in the previous bitmap. My 5 is going to be 0, 1, 0, 1. My 6 is going to be 1, 0, 0, 1. And my 7 is going to be 0, 1, 0, 1. So looking at what I've got here, if I was to shade this in, I know that I've got a 1. So I know that a 1 right here, that's this first block. So let me draw this little line so I can see where these 2 by 2 bitmaps are, these little mini bitmaps are. So I know where shading should happen. So I'm going to go down here, and first thing I see is that I see a 1 right there. Here's the 1, which means I should have no, yes, no, no. And then I've got a 2. So here's my 2, and I know that I see a 2 here. No other 2s here. So I should see this and this and this shaded. And then I've got my 3. So here's my 3. I see a 3 here. 3 is going to be just the top 2, so these should be shaded. And then I've got my 4. My 4s are blank. So anytime I see these 4s, they should be blank. So this is going to be blank. This is going to be blank. This spot here is going to be 5. 5 is this 0101. So whenever I see this 5, I'm going to see 0101. Then I see 4, 4. Then I see 4, 5. So that's again here and here, 4, 4. And now I'm looking at my 6s. So I've got my 6 here. And here I've got a 6 that starts off 1001. So this spot and this spot. And then I've got a 7. And I see this 7 right next to it is going to be this spot and this spot. think I made a mistake there when I was doing this, because I end up with the letter J, but I really should have had that spot there as well. This really should have been a 1 as well. Let me try and fix that real quick. This should have been a 1. Now notice that what we've done here is this process of shading. We end up shading everything we want. But again, we're looking at patterns to try and get these things to come out. And if any mistakes were made along the way, it's going to be glaringly obvious that we had the mistake, either because I don't have the correct number of pieces of data, or the pieces of data are in the wrong order, because I should see increasing numbers up to a point, and then I'll never see any number bigger than 7. And this is just another way of compression. In our next video, we're going to talk a lot more about parity, especially where we see parity in everyday life, and how parity helps us to figure out these errors, and in some situations, how to repair them. So once again, this is Mr. Potter. Thank you for watching. Have a great day.